We're back again. More office hours. Yeah. What I really should be doing is making more proper videos. Yeah. But I don't know. I don't know what I'm gonna make. I don't know what I want to make. That's not true. I kind of know what I want to make. What I really should be doing is making more proper videos. But today, I want to keep talking about D modules and stuff. So that's what I'm going to do. Yeah. So, where were we yesterday? Okay, I said something very silly. It was the original differential equation that we wrote down because I wanted square roots of functions. Hello, Arad. Yeah, I wanted square roots of functions. So, what am I looking at here? Let me go back up. What was our example? Yes. So we had this example of connection. Of a connection on, so we were looking at the non-zero complex numbers and the structure sheaf on there. And I wanted to look at this example of a connection. So basically it takes a function, spits out the exterior derivative of that function tensored with 1 minus that function over 2x dx tensored with 1. And yeah, I was being crazy and stupid, as one often does at this time in the morning. And really, this is the span of like x to the 1/2. Sorry, let me go back a second here. So computing the kernel basically results in, so say over this open set, well, over any open set, the kernel of the connection is going to be, in this case, just all functions on U which satisfy this differential equation. You just go plug f into here and see that it being 0 basically forces this. And so now if we look at the open set, in which we've removed the non-positive real numbers, this is basically x to the 1/2. And of course, if you've taken some complex analysis, which presumably if you've been following anything I've said on this topic, you have, then you know that this is basically because in order to find things like square roots and stuff, we need to choose a branch. So, yeah. And so the point is, though, this recovers a local system. In particular, it's locally constant, right? I mean, around U, or for this open set U, it's basically just this one-dimensional vector space, right? So it's basically, it's the kernel of this restricted to this open set is isomorphic to the constant sheaf on that open set. Is there a more geometric way to think about this? Like the push forward of a connection from the double cover? Well, there is, I don't know. Well, I don't know when you say this which specific part you're talking about, but I'm about to say something that will. So yes, there are like very geometric things going on here, and I'll maybe say more about that in a second. Um, I mean, to see that's locally constant, we need to know that for every point there's an open set that does this. But of course, we're only missing points on the non-negative line, so literally just pick any other branch, and that's how you get it. Um, yeah, but maybe okay. Let me step back for a second and maybe say something about where we're going. I'm talking about these are things I've been talking about lately with some people been studying things. Um, the point is that ultimately, I want to study, well, as some of you might know, some of my research involves perverse sheaves on a certain variety. And the Riemann-Hilbert correspondence the Riemann-Hilbert correspondence gives you an equivalence of categories between perverse sheaves and D modules. And I'm trying to understand this and the D module side of the story better so that we can maybe make use of some of those tools. And yeah. So the D modules though. So I should say in particular, I want to understand perverse sheaves constructible. I'll talk about this in a minute with respect to some stratification. Same with the D modules. In fact, it's more than just that they're constructible. It's that they're equivariant. So not only are these D modules and perverse sheaves on some variety, but there's some group action that splits it up into finitely many orbits. And so the thing is, I want to produce all simple D modules / perverse sheaves. Oh, I want to do a lot more than this, but this is definitely, one of the things, one of the starting points. And the point is that, I'll phrase this in terms of D modules, but it actually can be phrased in, there's this thing shows up on either side of the correspondence. So it turns out all your simple D modules are going to be of the form, so by L, I mean the minimal extension, which is a complicated thing that we'll talk about. In spirit, it's just some sort of push forward. So it's the minimal extension of what? Well, basically, you look at all of your orbits, and you look at all of the equivariant local systems on those orbits, and then you perform this weird sort of push forward thing. So, but that minimal extension involves taking a local system and understanding it in terms of D modules, and then performing minimal extension. And so, this thing I'm talking about here, so D modules can be understood in terms of connections. And so going back and forth, like taking kernels and getting a local system is going to be part of this story relating D modules and connections and everything. So this is where things are going. And so, I mean, it is very geometric, I would say. But there's even more geometry that I want to talk about first. So I talked about these equivariant local systems. How do we understand those? how do we know, how do we capture the equivariant local systems that we want? Well, the first thing to talk about is the classical correspondence of local systems. So it turns out that the category of local systems is equivalent to the category of complex representations of the fundamental group. And maybe we can go through this together in detail on stream. Or at least find, do some computations regarding the local systems we considered above. So how does this work? Well, the reverse correspondence, going from representations to local systems, kind of sucks. It's explicit. You can write it down. It's in like a char, for example. But the correspondence from local systems to representations is a little bit easier, in my opinion. So how do we do that? Well, here's the general. Well, there's two ways of phrasing it. You see, either you can do one of two things. I mean, it amounts to the same thing, but you just think about it differently. So you take a path, a loop in your space, and you take your local system, and then you can pull your local system back. You can pull your local system back onto the interval, and then you can take a stock at 0. But the stock at 0, I mean, that should be isomorphic to the stock of your local system at gamma 0, which is just equal to the stock of your local system at gamma 1. And then that, in turn, is isomorphic to the stock. Wait, am I doing things the wrong way? This is right, but somehow I want the same stock on both ends of this. Yeah, maybe we start here and then go through this isomorphism. Maybe I'll talk about it in the other direction, because I think that's the one I'm actually going to compute with. Yes, it's induced by the homotopy itself. Maybe I shouldn't have tried to. There's a way you can phrase it in terms of these pullbacks, but I'm going to do it in a slightly different way. Basically, here's another way to write it. You take a loop gamma based at x, and you take an open cover. Well, take a cover of this loop. Of course, this is the loop is compact because it's the image of a compact set. So you can choose a finite cover, and in fact, you can even choose one in the following way. So basically, you have, say, a bunch of sets like this. I don't know why I'm drawing so many, but you order them. U1, U2, U3, U4, U5, U6, and then you take points in the intersection. So x1, 2, x2, 3, so on, etc. And then the point is, so a local system is locally constant, right? So around each point, right, I can choose some open set. such that this is locally constant, such that the restriction, right, this is the constant sheaf. So in that case, the localization map down to its stock will actually be an isomorphism. And so what we can do then is string together. So using, we can basically, hello, Matthias. Starting at x, so x, our base point x here. We know that the stock at x under the localization map is isomorphic to L at U1. And then we can take the localization map down to the stock of L at x1, 2, right? So that's so we started at x. We took the inverse of the localization map to get an isomorphism with the sections here. Then we can localize back down to x1, 2, go back up to x2, 3, down to x u2, 3, x2, 3, so on and so forth, right? And so we basically play this game until we get all the way back to the stock at x. And in this way, don't worry, we'll look at an example soon. Or maybe I'll leave soon. I don't know. We'll do the example tomorrow. But ultimately, this results in, when you compose all of these maps, you end up getting a C linear isomorphism. And it turns out, I mean, this isn't obvious from what I've just written, but it turns out that this is independent. The isomorphism you get here of the homotopy class of the loop that you started with. In other words, this gives us the data of a representation of the fundamental group on the vector space being the stock of the local system. And it's exactly this process of sending of a local system determining a representation in this way that gives us the above-mentioned equivalence of categories. Your math book wants you to prove things are fields so many times and it takes so long you don't want to do it. Huh. Well, what book are you reading? Proving something's a field from the axioms probably takes a little while, but, you should probably, there's some theorems and stuff that you're using, right? Little bags of tricks that you're picking up on, so remember to keep those in mind, right? Like something like, the quotient of a commutative ring by a maximal ideal, or by an ideal, is a field if and only if that ideal is maximal or something, right? So I just say don't forget there's little tricks like that you should be building up. Yeah, once you've proven one or two things are fields from the axioms going through the whole list, there's no point in keep on doing that exercise. But you should maybe ask yourself, maybe they want you to be using other techniques to prove that something is a field, especially if it's taking a long time every time. In 2 months, you're starting a math journey. Nice. Least upper bound. Long time, no constant. I haven't had enough coffee to get that one yet. Yeah, okay, so let's look at this with our, let's see if I can do this explicit example live. So we've got our local system defined by this differential equation. Okay, yeah, I figured you were just saying hi, but I wasn't totally sure. Long time no see, long time no constant, yeah. And, well, we know, so we're looking at the non-zero complex numbers. So we have very nice... So, by the way, actually, should I do this all at once? Probably not. It's probably a bad idea. Yeah, I'll just stick with the simple example. Okay, so we have a nice representative for each homotopy class of loops, right? 2 pi I mt, right? So we've got these nice representatives, and we basically want to compute. We want to try and compute the representation corresponding to this local system. So, how are we going to do that? Well, we need a cover. So, what could we do? Oh, I don't remember my branch cut theory, so this is where things might go wrong. I wonder if my I should have had my good friend join me in these office hours, because he went through the computation in detail a couple months ago. Jose, if you're watching, save me. That's okay. I'm almost out of coffee, so maybe I'll end the stream and then do it another day. I'll have time to read up on it in between. You wanted to read Reed's undergrad algebraic geometry this week. In 1 week? That's not a lot of time. But you noticed your only algebra course so far was pretty group focused and decided to read some Alofi stuff. Yeah, that's not a bad idea. Yeah, you could also just go read Alofi's section on algebraic geometry first, and then you've got all the background details that you need there. And yeah, all the background details you need are right there, and then you can just go, fill in things that you're missing. Okay, so we're going to take 2 open sets. We'll take the open set to just be minus r less than or equal to 0, and we'll take v to be r greater than or equal to 0. And we'll just try and do these computations, right? So yeah, so let's see what happens. So I guess the localization map, so we'll look at the stock at 1 here. And so I guess we're trying to, look at LX, look at this isomorphism to LU, and then, we'll look at -1, We'll look at the isomorphism down to the stock at -1 and the isomorphism to LV, and then finally the isomorphism back down to LX. Hello, Edit Smith. So we've already seen that the open set at U, that this is the span of what am I writing? It should be L1. This is a span of x to the 1/2. So, and our stock, right? This is just going to be, this is all pairs, W, F, where F is in L of W, and W contains X. Right. Yeah, so I guess we already know, basically by this computation up here, we already know that everything in the second component is just going to be a scalar multiple of this function, right? So basically, just because we've chosen this branch, cutting out the negative x-axis, so we have a unique solution there. So really, for any one of these open sets, WF is just going to be equivalent to U alpha x1/2, right? So that part of the isomorphism is pretty well understood. But now, I guess we then want to think about the localization map going to -1. And this corresponds to taking the other branch cut here. Yeah, actually, I'll probably want to think about this offline. And I am out of coffee, uncoincidentally. So maybe I'll finish this computation tomorrow and call it here for today. Well, maybe I will say one thing before I go, though. So we should expect, we know what the fundamental group is, right? We know what the fundamental group is. Right? It's isomorphic to the integers. Right? I said we have these are our representatives for each homotopy class, one for each M in the integers. So definitely, what are our irreducible representations? Well, one, certainly we have our characters of this group, and those are, we have ones of the following form for each M. We have the quotient to Z mod. Oh, no, I picked an M and an N earlier, so I don't know. Let's say Z mod K, just to avoid any of the symbols up above. And then, we have this is a finite abelian group, and so all of its irreducible representations are characters. And, we can totally understand each of those. So basically we have representations of this form, and these should correspond to local systems. And so, okay, next time we'll go through and we'll see exactly what these correspond to.